Hello, and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 230, Kth Smallest Element in a binary search tree. Given the root of a binary search tree and an integer k, return the kth smallest value, one indexed, of all the values in the nodes of the tree. For example, if we're given this tree here and we're asked to find the third smallest element, we should return 3, because the smallest is 1, the next largest is 2, and then the third largest is 3. So how do we want to do this? Well, there's two ways to do this problem, and we'll start with the naive solution. The naive solution is to simply perform an in-order traversal of our binary search tree. And if you don't know, an in-order traversal of a binary search tree will actually give you the elements in sorted order. So if we do this, we'll get a list back with 1, 2, 3, 4, 5, 6, right? That's the elements, and then we just take the, whatever we're looking for. So we take the third largest, which is going to be at index 2, right? Because we're looking for the value is 1 index, but our array is 0 index, so we need to subtract 1 from whatever the value is to find our answer here. So we would return this 3 here. So how do we want to, that's the naive solution, right? But your interviewer is probably going to ask you to do it in a different way, which is for you not to actually traverse the entire tree because it's not really necessary. What we can do is actually perform the in-order traversal, but instead of having to do the entire traversal where we go here, then here, then here, then back here, up here, we can actually stop once we've seen k elements in the in-order traversal, and we can, simply return whatever that kth element is. So if instead of doing this recursively where we perform the, depth first search to do the in-order traversal and get all of the elements, we can do it iteratively and simply do an in-order traversal using, a stack as we would with the iterative method, and simply stop once we've processed 3 elements from whatever the smallest element is here. So that way we're going to get our third largest without having to actually process the entirety of the tree. Because if the tree is really big, there's no reason to do the entire thing. We can just stop once we found whatever our, kth smallest element is. So that's how we're going to want to do it to kind of satisfy our interviewer. So we're just going to do this in an iterative manner and stop when, we've seen the kth smallest element. So let's go to the code editor and look at how we might do this using the in-order iterative traversal. Okay, we're in the code editor. Let's code this up. So in case you don't actually know how to do the iterative or you forget how to do it, I'm just going to talk about the naive solution. So at least if you get this in an interview and you forget the optimal solution, then you can code up the naive one. So what we want to do here is we want to just do an in-order traversal. So we're going to say, elements equals self dot in order, and we're going to pass in the root, and at the end we just want to return elements of k minus 1. Now let's define the in-order function. So we'll say def in order. Just going to take self and a node, and there's actually a really nice one-liner for this in Python. We're going to say return self dot in order node dot left plus the node dot val here plus node self dot in order node dot right if the node exists. Otherwise we're going to return an empty list, and that's it. So let's run this, make sure we didn't make a bug, and we can submit this and see that it works. But this isn't the most optimal solution. And just to recap the time and space complexity here, we're doing an in-order traversal, which means that we touch every single node. So that's going to be a big O of n, where n is the number of nodes in the tree. And space complexity, we need big O of n because we have to store all of our elements in this elements list. So let's take a step back and actually write the code for the iterative in-order solution. So to do that, we're going to need a stack. So we're going to define our stack here. And now we need to process our, tree and basically find that kth smallest element. So what we're going to do is we're going to be processing. So we're going to say while true, and we're always going to break out of this, so we don't have to worry about, the infinite loop that we're basically writing here. So we're going to say while true, we're going to say while we have a root, so while we have something to process, remember that in Inorder Traversal, we try to go as left as possible. So while we have a node, we're going to try to explore it going as far left as possible, because in a binary search tree, going as far left as possible will be the smallest element. So we're trying to reach the smallest element and then undo our recursion from there. So, for example, if we had this one, if we're given the root, we obviously want to go as far left as possible. So while we have this root here, which is the node that we're working with, we're going to say stack.append whatever our root is, because we need to process that at some point later on. And we're going to say root equals root.left. And essentially what we're doing is we're going to the left, and we're going to go to the left, and we're going to go to the left until we hit basically the leaf node, which is the smallest one in the tree. At this point, what we want to do is we want to say root is now going to be whatever we pop from the stack. So stack.pop. And then since we've now seen an element, we want to decrement our k by 1. Because once we get to this point, that means we've gone as far left as possible. We're at the smallest node that we can. And essentially what this means is that we now want to start counting up from whatever the smallest is until we get to our kth smallest. And we're going to go through the process in this loop. And the last thing that we need to do here is actually check if not k. So basically if k equals 0, that means that our current node was the one that basically took us to k smallest element, and therefore we need to return the root. So we can simply return root.val, and we are done. Otherwise, in an Inorder Traversal, what you do is you go to as far left as possible, then you process the current node, because it's in order, right? It's going to be left, the current node, and then we need to go as far right as possible. So we're now going to say root equals root.right, and then basically this loop will go again, because obviously it's an infinite loop until basically we find the k, which is guaranteed to exist in the tree. We don't have to worry about this never returning, and then we'll just go through this process until we find our, kth smallest. So let's just run this, make sure we don't have any syntax mistakes, and submit it, and we're done. Okay, so let us talk about the time and space complexity. In this problem, doing it this way is actually not any faster in the worst case than the naive solution which we did before. And the reason for this is, if we were given a tree that we could be given the case that our kth smallest, our k here, is actually going to be the largest element in the tree. So we could end up having to process the entire tree anyway. So in that case, we could still, in the worst case, which is what we use for these time complexities, see a big O of n runtime. Although in the average case, it's going to be much faster, and it's going to depend on, I guess, how close this k is to the smallest element. So, if we see 2, then obviously it's going to end a lot faster than if we see k, where k equals to the number of nodes in the tree. So it really depends on what k is, but in the worst case, it's still going to be big O of n. The space complexity, because again, we're using a stack here, and we could potentially have to store the entire tree in the case that k basically equals the number of nodes in the tree. Because we could have a very skewed tree where it's like all one side, we could end up storing all of the elements in our stack as we do the traversal downwards. So for that, it's also going to be big O of n. Although in the average case, again, it's going to be faster than our previous solution, because typically k is not going to equal the number of nodes in the tree. It's going to be somewhere between the first node and the number of nodes in the tree. So we can kind of consider it as like n over 2. So in the average case, it's going to be faster. But asymptotically, the two algorithms are technically the same. You will probably be asked to implement this solution because the other one is a little bit too simple, and your interviewer is probably going to want to know that you can actually do an in-order traversal iteratively. The recursive solution is like way too easy, and as you saw, there's a one-liner to do it for you. Your interviewer is probably going to want to know that you can do it using a stack, because this actually tests your knowledge of the in-order traversal, of how you go to the far left as possible, then you process the node, then you go into the far right. So typically when you see questions like this, don't be surprised if your interviewer says, actually, I want you to do it iteratively, because I think that way it shows more of an understanding of how the algorithm actually works, as opposed to, again, memorizing that one-liner that you can use in Python, and it's basically cheating. So that being said, that is how you solve this question. Not the most complex one, but still a really good one to know, and I think it's a quite fun question. If you enjoyed this video, please leave a like and comment. It really helps with the YouTube algorithm. If you want to see more content like this when you're preparing for your on-site interviews, please subscribe to the channel. I have a ton of resources that should help you with your on-site and Leetcode preparations. Otherwise, thank you for watching this video and have a nice day.